Good morning, class. And by class, I mean you, Joe Sock Fourier. How are you doing today?
I'm doing great, Dr. Rock. I was just washed and dried last night, and I feel so excited to learn math today.
Wow, that's amazing. Well, Sock, today you're in for an amazing treat because we're going to talk about everybody's two favorite partial differential equations. We have the heat equation and the the Black-Scholes equation. Sock, you see what I did there?
Oh, Professor, you're pulling out all the sock jokes today, aren't you?
Okay, so let's start, shall we? So the Black-Scholes equation is it's a pricing model to determine the fair value of a call option based on variables such as the stock price, the time, the strike price, the volatility of the stock, the risk-free interest rate. So here's the Black-Scholes equation. It's a second order partial differential equation where you have the first partial with respect to time and the second partial with respect to the stock. So let's see if this works with an arbitrary function. So Stock, can you give me a function that we can try to take the derivatives of to fit this equation?
Let's start with the function s, which would mean that the price of the option is only a function of the stock price.
Awesome, exactly. I like how I said stock price there, not stock price. That's pretty funny. So let's say our function f is a function of s and t, but we're just calling that s, right? So if I went through the partials here, Stock, what is the first s partial of the function s?
What?
The one, exactly. Okay, and so if we take the partial of that partial, what's it gonna be?
0.
Exactly, because the derivative of a constant is 0. Okay, awesome. So now we need to talk about the t partial. So if our stock price is just a function of s and not t, our t partial will be what?
0.
Awesome, there we go. So we have these three things here, and now let's start substituting them into our equation. So ft is 0, so we'll have 0. Fs is 1, so we'll just have minus Rs plus 1/2 sigma squared s squared, but our second s derivative is 0, so that all goes to 0 as well. Lastly, we have minus Rf equals 0. So now we ask the question, does Rs minus Rf equals 0? Yes, and tell me why, Sock.
Because the function f we defined to just be s.
Right, exactly. So lastly, we're going to plug in s for that f down there, and you get Rs minus Rs equals 0. And obviously 0 equals 0, so we proved that the Black-Scholes equation will work for the function s. Now,
We have a student joining us from Zoom today. Hello, Joe Sock. How you holding up?
I'm okay. I'm a little sick, but I'll be better.
Awesome. Well, I'm sure that in quarantine over there, you've got nothing better to do than learn about so much more math than usual. So to kick things off, would you mind telling us a little bit about what these initial conditions mean for the Black-Scholes equation?
Sure can do. So the first one is saying that the call option will be worth at most S minus K, where S is the stock price and K is the strike price, if we exercise our call option, or it'll be 0 if we do not use the call option. The next assumed condition is if the stock price equals 0, our call option is worthless. Duh. And then finally, the last one comes from the put call parity formula, which is a put option equals a call option minus the stock price at t equals 0 plus k e to the negative rt minus t. If we use a call option, p is 0, and then rearranging by using some algebra, we get to that final condition.
Awesome. Thank you so much. And remember, as you told us last time, this t minus t is equal to the expiry date, right?
Yes.
Awesome. Okay, so now let's talk a little bit about the change of variables that we'll have to implement to get from the Black-Scholes equation to the heat equation. So first, we're going to let u equal the natural log of s, and we're going to let v equal this expiry time t minus t. And we can use the multivariable chain rule as well as the product rule from calculus to see that this partial derivative will get us 1 over s del f del u. And here to get the second partial derivative FSS, we're gonna get this little expression here. And then again, we can find this partial differential, and then we can substitute all of these values into the given Black-Scholes equation. And then we'll reorder things a little bit and see that del F del V is equal to this. And then we can factor that out a little bit. And then things are beginning to look a little bit more familiar. Josok, can you answer this question? What does this look like to you?
A quadratic equation.
Yeah, you're totally right. And so we can see that it's not just a quadratic equation, but it's also a partial differentiable equation, right? And so we're not necessarily used to these coefficients, so we want to make it a little bit more simple and familiar. The goal is the heat equation. So to do that, we're gonna have to define some more multivariable functions. And here, because we love Greek letters so much, we've chosen phi and psi, two functions in terms of x and t. And so they're defined here on our slide. And then using the similar rules with multivariable chain rule, all that good stuff from calculus, we can see that these partial derivatives are as follows. And then we can put everything in terms of psi, and then we'll see that psi sub t is equal to this expression here, okay?
And then lastly, our goal is to get it to the heat equation. So if we try to set alpha and beta equals to the coefficients of our x partial and our regular function psi, when we do that, the x partial of psi and the psi function itself will go to 0, and we're left with the heat equation.
Yay, indeed. Thank you so much, Josok, for all your help. Make sure you're staying healthy out there, okay?
Will do, thank you.
Awesome. Well, good luck with the rest of your quarantine. Happy healing.
All right, Joe Sock, I'm glad you're feeling better, but I think you owe me an explanation. We just talked about for a little while how we can get from the Black-Scholes equation to the heat equation, but I need you to tell me how we can do it the other way, so please enlighten us.
So once we're at the heat equation, we can actually use a Fourier transform, which we've been doing quite a bit recently. And we'll do that with two variables that are given in the conditions. So we're using x and t. And we'll write the Fourier transform in terms of x, where t is a constant. Then we'll get an ordinary differential equation with t. So then we can solve the ODE to get a solution with a constant.
Right,
and
yeah.
then we'll use the initial conditions to find that value of that constant.
Oh, okay,
Yeah.
that makes much more sense to
And
me.
then we can use the inverse transform of the solution to get a convolution integral. And then we'll evaluate it.
Right,
Yeah,
yeah.
complicated stuff, I know.
Definitely.
And then we'll check the boundary conditions and make sure they're satisfied. And
Okay.
then at the very end, we can change the variables back to the S, T, K, sigma, R, all that good stuff.
Right, so we can get it finally back into the financial variables. Okay,
Right, and then that would set us up so nicely to do an example, right?
yes, and then now in the video, let's see that example. So now, after we magically got to the Black-Scholes equation, we're gonna use it and do an example about some company. Let's call it a sock company. Why not, right? Good idea, sock?
Of course.
So here's the example. We're gonna find the price of a call option if the stock is worth $43, but we want to buy a call option at the strike price $42. There's a risk-free interest rate of 11%. The volatility of the stock is 0.25, and our call option will be valid until for 4 months until it expires. So here's the Black-Scholes equation, and we notice here that we have some variable W. Sock, what do you know about this W variable?
W is actually the first derivative of the call option with respect to the stock price. When we magically arrived at this formula for the price of a call option, one of the steps along the way would have allowed us to take the derivative of the call option function, allowing us to find out W. Fun fact, W is also equal to delta, which is one of the Greeks in finance.
Yes, it is. It's one of the Greeks of finance, which is the financial derivatives. Good job, Sock. You hit the sock on the foot. But yeah, looking here, we can see that we're trying to find the phi of W, which is really a probability. It's the standard normal CDF. Okay, so now all we need to do is just plug in all the numbers into the variables. But can you tell me how I can express that expiry time in our equation, please?
Since our call option expires in 4 months, which means we'll be able to buy the stock at our strike price, 42, for 4 months, hopefully our stock will go up a lot. But anyways, we can write 4 months as 0.33 because 4 months is a third of a year.
Good job, Sock. Now let's do the math. So, we plugged in all of our numbers into the variables in the Black-Scholes equation. We took the CDFs of W and W prime, and we get the value for our call option. Anything you want to add, Joe Sock?
I forgot to mention last time when explaining what the expiry time meant that not only do we express it as 0.33 because 4 months is a third of a year, but also in the function that's given to us, the Black-Scholes equation, the big T minus T is what refers to the expiry time, not just T.
That is a great point, Joe Sock, and I'm sorry I didn't mention that earlier. That's why you're a good student. Lastly, we realized that our call option is worth $3.84, so that means that it would be valuable to buy a call option on the Sock company. So, Joe Sock, what do you want to say about this?
Well, you know how those positive call options make me feel. I'm going to buy so many units of Sock stock so I can buy all the Fisher Black stock and Myron Scholes stock to bring to class with me tomorrow.
Ta-da!